Hello, welcome to this session here at DVCon 2021. I'm Michael Young, the Palladium Product Manager.
And I'm Juergen Jaeger, the Protium Product Manager. Together, we will guide you through this tutorial and discuss what the benefits of a common methodology for emulation and FPGA-based prototyping can be for you and for your projects.
Okay, so now let's take a look at the system and the chip design trend looking forward through 2025. Some of the obvious factors like time to market, maintaining the development cost, or at least make it as efficient as possible. The desire to have these multiple cores in a design, especially in some of these hyperscaler or AI design. And of course, the complexity around that is going to drive the workload to be much higher, as well as the integration of existing IPs as well as new IPs. And this will, of course, create the traditional problem that you have in validating the design. All that is still nothing compared to the software stack that you need to develop on top of this SoC that eventually goes into a PCB board that's going to have communication to other chips around it. And this is going to create a lot of workload and validation workload. And customers are trying to do this in a pre-silicon manner so they can get their design done right the first time. They want to reduce the spin. And they also want to reuse the environment as much as possible. So as you can see, more than 80% of the design in this space from the IP perspective are being reused, and about 60% of the software is really needing the effort required to complete the silicon along with the software so you can deliver this product. Now, if you put this in a chart, this is basically the node in which you're going to design your silicon. And you can see that exponentially, the cost of developing the chip is growing. Not a surprise there, hopefully. But what's really surprising is the cost of software development and the verification is now going to be more than 50% of the chip development. And so knowing where to attack and knowing where to focus is going to basically help you make yourself more efficient with your organization. And software, again, is necessary to create this design. You can't just sell a piece of silicon anymore. So any delay in software delivery essentially delays your product. And see, here's a model that you can see. From a source from IBS, you can see that from a 3 months, 6 months, 9 months, and 12 months perspective, what is the impact of potential revenue loss based on the different market windows, whether you're on a fast-paced market, medium pace, or slow market. So you need to start to think, designing silicon is also now, you need to think about how fast you can develop your software as early as possible, and making it into pre-silicon is now the name of the game.
Emulation and prototyping, while sometimes considered expensive, really pay for themselves. They dramatically accelerate time to product and therefore time to revenue. What you see here on this slide is one example of one of our customers where their use of emulation and prototyping reduced the time from first silicon bring up to release of their product from 75 days to 15 days. That's a reduction of 2 months. They were able on emulation and prototyping to start embedded software and firmware development early, do the hardware software integration all while the silicon was being built. Now, 2 months, you may say it's not that much, but just do the math. If the annual revenue of your product is, let's say, $100 million, then every day is about $300,000. 2 months are $18 million. You can buy a lot of emulation and prototype systems for $18 million. So it really pays in the end to have emulation and prototyping. Not only does that increase the quality of your product, it actually increases the revenue and your time and path to revenue.
Right. So now let's look at the behavior of how customers sees emulations and prototyping. So what the customer cares about in the emulation side is really about design, debugging your design. And what you really need to have is a predictable and fast model build. Now, this allows you to basically have 1 to 2 or 3 even turnarounds per day. Because as you're discovering these bugs, you need to fix it, you need to run through the ECO process, and so you need to have a very predictable way to rebuild it. And emulation is really a very good vehicle, especially with the Palladium, because it's a processor-based engine. So the process is actually quite predictable in terms of the compile time. Next is you need a system that is scalable. So customers, don't just do full chip emulation from the get-go. They're going to have, IP level modules and subsystems and all the way scale out to the full SoC. So you need a platform that are able to run fast enough from IP all the way to full chip. And you also need a very good engine for you to debug on. So you need very fast intelligence. You need to have good traceability. You need to have ability to control your triggers and have all flavors of instrumentation put in. Now, from the prototyping perspective, your focus here is all about debugging or validating your software on top of a pre-silicon environment. And prototyping is really one of the best vehicles for you to do that, because you get to do this much earlier in the design cycle. You're looking at, a build time and a debug are less important because you're not trying to iterate through 2 or 3 RTL models in a day, but what you're trying to do is iterate that through maybe once or maybe once every 2 weeks. That's kind of the level that you're at that time. And so then the SoC and the subsystem capacity is what you're mostly interested in, because you need just enough hardware fabric to run your software, right? And you need sufficient sufficient performance so you can run your software debug, which obviously requires much more longer runtimes. And to think about the benefit of bridging these two platforms, emulation and prototyping, we've been investing a lot on what we call a common compile, a common debug, as well as a common solution through hybrid, virtual, or accelerated VIP. And by doing that, you're able to bridge the gap between emulation and prototyping, and you're going to have some very interesting and efficiency that comes out of this.
Having both emulation and prototyping at your disposal enables you to use the right tool for the right job and at the right time. This graphic you see here actually also reflects what our customers are doing in real life. Early on in the project cycle, an emulation system like Palladium Z1 shines and helps you to get the chip design right and the RTL ready and clean. Important aspects of that are that you want to have a fast and predictable build and compile time, superior debug capabilities, and of course performance that exceeds what you can achieve in simulation. So in emulation, you can easily achieve 5,000 times faster performance compared to a simulator. And if you go into in-circuit emulation mode, you're really running typically in the megahertz performance range. Palladium also shines in use mode versatility, with over 20 different use modes available to you. And on top of that, the capacity to implement even the biggest multi-billion gate designs. Once the RTL is more complete and more stable, the user wants to run more software and of course also longer hardware regressions. Therefore, it then makes sense to add FPGA-based prototyping like Protium X1. Protium X1 uses the same compile flow as Palladium C1 and makes it easy and fast to bring up a design. At the same time, X1 provides an additional performance boost, often in the 3 to 5 times faster than emulation range, and that at a lower price point. An additional unique X1 capability using native interfaces like PCIe or Ethernet or USB can even further improve the execution speed of software on a Protium system. So using the combination of both now enables you to stay on schedule with your project or even accelerate it. Emulation and prototyping are around for over 20 years already. So why would we need a common methodology now? To say it bluntly, because the old ways of doing emulation and prototyping just don't work anymore for today's and tomorrow's designs. We don't try and drive on the Autobahn with an ox cart. We use a Porsche or a BMW if we want to go fast. Today's designs have too many gates, too much memory, too many interfaces, and most importantly, too much software for traditional methodologies to be able to do the job. And on top of that, you often don't have enough time. So you need something that allows you to accelerate your schedules. While Palladium and Protium, each on their own, are best-in-class emulation and FPGA-based prototype platforms, together they are truly unleashing the potential of what the user needs to successfully develop their products. Each of them has their own strengths. Palladium has its core strengths in SoC, meaning hardware chip verification, from fast bring-up to market-leading debug productivity. Protium, on the other hand, with its superior performance, has its core strengths in fast pre-silicon software bring-up and hardware-software integration. Common to both are the implementation flow and peripherals like speed bridges, accelerated verification IP, which in return enable customers to quickly transition from Palladium to Protium. This dynamic duo, as we commonly refer to the combination of Palladium and Protium, offers the best of both worlds. Moreover, it allows for a seamless transition between emulation and prototyping, including the reuse of peripherals and testbench environments. One of the key benefits of the dynamic duo, as mentioned before, is the notion of a unified flow. Once the Palladium environment is set up, the reuse of that existing environment for Protium and vice versa is easy and fast. For example, things like clock mapping, memory models, compile script, even additional solutions like accelerated verification IPs, speed bridge adapters, software models, all are compatible and reusable between the two platforms. This now provides the functional congruency between emulation and prototyping and allows difficult hardware bugs to be debugged in emulation, while software issues can easily be identified and debugged on Protium. We also introduced a common compiled front end, which will eliminate learning curves while providing common language coverage. As an additional benefit, new front-end capabilities, fixes, new capabilities, new features are decoupled from the backend of the respective platform. Like, for example, in Protium case, FPGA plays a node. So enhancements can be made available almost instantaneously, and it will work on both platforms at the same time. Again, one of the benefits that now allows you to really take advantage of the unique capabilities both platforms have in a common, consistent, and congruent way.
Right. Thanks, Juergen. So we just talked about the common methodology and the common flow and compile. Now I'm going to dive in a little bit about what Palladium does for our users. And so there's really different aspects of Palladium. One is the ability to do multi-user and sharing the resources that you have, accumulate over the time that you have assembled for various projects. And so the way to look at it is a system that you have purchased, and you put it in your data center or in your lab. You can do sharing between projects. You can do sharing between the engineers within the project. You can allocate the resources based on their priorities. And then you have different ways to connect to the system. So many of the users are in fact not local to the lab. Many of us are now working from home. And similarly, our emulation engineers and our customers are also able to access this resource remotely. And so here's a kind of a virtual way to represent the resources available in the Palladium. So each of the little blocks here or the diagrams representing a capacity that's available. You can assign certain capacity to a particular user or jobs. In this particular scenario, we're like indicating there's a physical connectivity to this blocks here for in-circuit emulation. And then on this side, we have transaction-based accelerations, and you got different users in different sizes. So this is one of the core strengths of Palladium, where we are being shared among different users, and it's being scaled up, right? On the other side, it's about use model versatility, because the Palladium in servicing the various users, we discovered that there are different workloads and different activities that has to happen. And so what we want to do is have core emulation, things like in-circuit emulation, virtualization, architectural trade-off analysis, low power, post-silicon, hardware, software, and simulation acceleration to be part of that arsenal when the customer have a need. Now, I have to say that most customers probably use 2 or 3 of these use model, and not all of them uses the 22 use model that we have been tracking. But nevertheless, it gives them the ability to grow in the future. And this is key in the, basically maximizing the resource that you have. Now, let's take a look at the Palladium Z1 characteristics. Palladium Z1, this is basically showing a rack formation in the data center setup. Its ability to scale from 4 million gate to a little more than 500 million gates on a per rack basis. The rack can be scaled, meaning they can be cascaded to make it monolithic, and you can scale all the way up to 9 billion gates with more than 2,000 users being able to share the resources. Because it is a rack form factor, it is very convenient to set up in the existing data center. It also has built-in redundancy, so you get high reliability and high uptime. These are some of the metrics for the rack. I talked about the user capacity. There are dedicated user memory and dedicated debug memories for you to use as part of the emulation. And of course, the debug memory is for us to track all the results that you have. We also have very high bandwidth. There are 56 gigabits per second ports, and you have as many ports as you need to connect to your host. The maximum performance that we do anticipate is up to 4 megahertz, and of course, your performance will vary depending on your design size and what is your use mode, what is your interfaces. And so, but on average, we see anywhere between 1 to 2 megahertz for our customer base. We also see up to 140 million gate per hour in terms of a compile. And again, that depends on your workstation that's been resource available within your company. and lots of I/O for in-circuit emulation, probably more than you would ever need. But this is really about sharing capabilities between the users. On the virtualization and solution front, we have a unique position to do virtual target relocation. And so that means you don't have to physically go into the lab and move some of these, I/O cables. It would be just virtually relocated for you depending on your needs. We also have this advanced job reshaping. As your jobs move in and out, so you can imagine that you may have some fragmentations or holes in the fabric, but we have the ability to kind of reshape your job so that it will fit into the open fragmentation so that you can still take advantage of open slots. Emulation Development Kit is really making your job to interface with PCIe, USB much simpler by basically offering you a complete kit and virtualizing that experience, as well as offering virtual emulation through our accelerated VIP, and of course some customers really like to do virtual debug rather than a physical JTAG. We can also do now virtual debugging through this interface. So a lot of good virtualization around this, which enables you to do a lot more remote work. Now let's take a look at the Palladium use modes. There are 4 main use modes, which is different than use models. First one is in-circuit emulation. So this is a physical connection to a speed bridge, which is basically our speed gasket or adapter to a physical interface like a PCIe or a Ethernet or SAS or SATA, etc. This is probably by large one of the most popular solutions that we have out there. And then on the right-hand side, simulation acceleration is really for the user base that really wants to improve their simulation performance. And so then you can do a connection either through our accelerated VIP, and again, depending on your interfaces, you could have a variety of different protocols. And then you can also connect it either to a C test bench or a UVM test bench. On this side, you have virtual emulation and virtual bridges. This is allowing you to, instead of physical emulation, you can do virtual emulation through our virtual bridges. And then last but not least, some customers actually prefer what they call synthesizable test bench, essentially moving all the stimulus and all the control mechanism inside the hardware, so then you can embed your test environments for full control. And of course, this allows you to run your design at the fastest speed without any interruptions from the host, right? So it's kind of have a similar performance gain as a in-circuit emulation. Now let's put this in actual context from a use modes around that environment. So this is kind of summarizing the 4 different use modes. But on top of all this stuff, I think it's important to highlight that one, Palladium has a very fast compile objectives for small, medium, and large designs. We have what we call FullVision. You have the ability to see every signals, every traces in your design. We also provide functional coverage, code coverage, and you can also add assertions. So this is about adding intelligence so that you can monitor your designs. Of course, multi-user, ability to share the resource. And then, of course, some customer cares about low power verification. So you may have power domains in your design, and you want to use UPF to control the power domains to come on and off. At the same time, all these capabilities can be applied while you're trying to do some power analysis, what we call dynamic power analysis. So you can extract the information that you need for you to do some optimization with regards to power and performance. Okay, some customers actually even run benchmark on top of the design, and they'll look at the power results from that. Again, the test environment would be going through a virtual interface. So when you do simulation acceleration, this is where your test bench are residing on the host side. Your DUT is sitting in the Palladium. Similarly, on the virtual emulation, this is really about now running your design either with a companion virtual device models or some sort of application, or let's say, a 4G or 5G testers in a virtual environment, you can drive that stimulus through that interface into the Palladium and getting the result back for checking. And on reverse, when you have the physical interface through the in-circuit emulation, this is where you physically, put in a host environment where you can bring up the operating systems, the applications, and so you're going to get as real as possible to the test environment you're going to be in. This is, going to be very representative of your motherboard that you're going to have with your SoC on board. Okay. Now, next, we're going to talk a little bit about the Palladium debug. So Palladium is really well known for its debugging productivity, and you don't lose any speed, right? So if whatever speed that you get running at Palladium, whether you turn it on or turn it off in terms of debug, you're going to run at about the same speed. So we offer FullVision, which is basically seeing design at any signal that you want at full speed. You can do dynamic probes, which is really good for a select set of traces that you want, but it will give you a much longer visibility. And then for customers that are needing even more trace depth, they can turn on the infinite trace. And then, of course, there's a whole bunch of other debugging techniques like offline debug, waveform streaming, save and restore. This is really good, especially when you're doing, let's say, things like operating system boot up, OS boot up, and then you want to run some application on top of it. So instead of rerunning the OS boot again and again before you can run the app, you can actually save the state of the operating system boot, restore at the point where you have a clean boot, and then you run your apps, right? So this is not just about debug, but it's also about improving your productivity by snapshotting into the right location. We also have the ability to hot swap from simulation into the hardware. This is, again, a very unique capability that we have. You can force any particular design state that you want, whether it's a register, a trace on a wire, and you can analyze the behavior based on some special condition that you want to do. And this is outside the test bench or the in-circuit stimulus that you may have. Then, of course, we have SDL and dynamic RTL. So the state description language is the ability for you to create very complex trigger conditions. You can change these conditions without having to recompile the design. This is very useful in basically triage the bugs that you have. So overall, we're providing very good control and very good visibility depending how you want to use it. And we're typically much better in terms of getting a good turnaround time for our customers in isolating and turn around their bugs. Now, all that is really fundamental in emulation and debug. But I also want to really emphasize the methodology that has been in place in simulation world for a long time, where they're tracking through assertions and functional coverage or code coverage, allowing themselves to basically track what is the progress of my design, how well are they behaving, am I testing in the right area? So the same methodology has been extended and put into emulation. And the result of that is now you can do more intelligent runs. You don't necessarily need to run 100,000 tests if half of them provide you the same coverage, right? And so you can be smart about this. And not only that, the coverage that you have, if you have Xcelium, you can actually also merge it with the result from Palladium. So now you get a much broader coverage model than what you would do if it's just running by itself. And all this capability can be visualized either in our IMC or vManager, right? So this is all the goodness in providing that level of intelligence.
Thank you, Michael. Very impressive. I hope everybody got a good feeling of what Palladium can do and how it can help you. Now, let's shift gears and take a closer look at FPGA-based prototyping. Cadence is a relative newcomer in prototyping, which can be good or bad. Bad because we are late, of course. Good because we started with a clean slate and could create a solution that best fits our customers' needs. And the result of that is the Protium X1 enterprise prototyping system. When the previous generation, Protium S1, was introduced in 2017, it marked the first significant innovation in FPGA-based prototyping in more than a decade, by reducing bring-up time by an average of 80%. With Protium X1, we have further expanded on our technology leadership with the introduction of the industry's first scalable data center optimized enterprise prototyping platform, architected from the ground up for scalability and flexibility in a data center optimized form factor. With Protium X1, we are addressing the 4 major user requirements and challenges: high performance, scalable capacity, very fast bring-up time, and a lot of debug capabilities and therefore debug efficiency. FPGA-based prototyping for many, many years has the reputation, and rightfully so in many cases, of being difficult and time-consuming to bring up. That has changed with Protium X1. Think about a smartphone in your pocket. Without the software and apps running on it, it would just be a paperweight. Similarly, what makes Protium X1 so efficient is our industry-leading implementation and debug software. Yes, the hardware is impressive too, but what really makes it work is our implementation software. And that ensures that your FPGA-based prototype comes up quickly, reliably, and has all the debug and interface capabilities to start firmware and software development as early as possible. Now, designs come up in days or weeks, not months, as in traditional prototyping. Take a look at the graph on the left side of the slide. This is actual user data. It was not generated in-house. This is feedback from our customers that migrated and upgraded from traditional prototyping solutions to Protium. And in traditional prototyping, a multi-FPGA prototype, in average, as you can see here, takes about 20 weeks. 20 weeks, that are 5 months. It takes you 5 months to bring out a prototype system. Yeah, it runs fast in the end, but it takes you a long time. With Protium, the average bring-up time is less than 2 weeks. So you save over 4 months of bring-up time. And that, of course, can translate into higher quality because you have more time to run your verification, but also faster time to market. It also enables an easy transition from your emulation to your prototyping environment. So here we are back to this common methodology for emulation and prototyping. Responsible for that is that mapping ASIC memories into FPGAs, for example, have always been a major pain point in prototyping. We have eliminated that pain point once and for all with our unique memory combination and modeling technology, again, common between Palladium C1 and Protium X1. And that now enables our users to automatically map any and all memories into Protium X1 automatically. And let's not forget all the interfaces we have around it. We provide a rich portfolio of speed bridge adapters for all common interfaces and protocols like PCIe, USB, Ethernet, MIPI, and so on. So now that you can run your design real fast, and you got it to run really fast, what to do if things don't work as expected? After all, your design is still under development, and prototyping is a verification tool. So to help with debugging a potential we have added an elaborate set of debug capabilities. Of course, we can do the usual things like probing and creating waveforms. Everybody can. But then we have also added more simulator and emulator-like capabilities, being able to force internal signals into zeros or ones, often used to configure a design, to do what-if analysis, failure analysis, and so on. We can monitor key signals in real time, capture tens of millions of user clock cycles with our high-speed data capture card. And most recently, we added prototyping full visibility, which provides now dynamic access to all signals in your design without recompilation. And that, of course, also improved the overall verification throughput. You can almost look at it now as kind of a simulator when it comes to hardware verification. Another interesting aspect of debug is the software side of things. You're running software on top of your design that you implemented, your chip that you implemented in Protium X1. And software developers usually don't think in forms of waveforms or probes. Software developers need a different set of debug tools. They need the ability to connect their software debugger of choice, often through a JTAG port. They need the ability to access any memory in the design, read and write to that memory, look what is going on there. They need to be able to set breakpoints, meaning stop the clock of the design and resume again. And in some cases, having a transaction interface to directly connect to software models running on a connected host workstation. All this is supported and available on Protium X1 and makes it both a high-performance hardware regression and verification system, as well as a highly efficient software validation and bring-up solution. So far, we have mostly talked about big designs, but not all designs are billion-gate designs. What if somebody just wants to prototype a subsystem or a piece of an IP? Even the biggest design starts with smaller blocks, IP, and subsystems. And we have a mode for that too. Protium X1 is not only enabling the prototyping of billion-gate designs, but it also offers single FPGA granularity and multi-user capabilities to run jobs on the exact number of FPGAs needed to maximize system utilization and efficiency. What you see here in this picture is what we call the X1 blade. The blade has 6 FPGAs on it. And so on a blade, you can run up to 6, you can have up to 6 concurrent users all running the same design or running different designs. And now extrapolate that to the whole rack, which you saw in other pictures. A Protium X1 rack has 48 FPGAs in it. So on a rack, you can have up to 48 concurrent users all working on the system independently. Aside from the common flow, another highly valuable characteristic of the common methodology of Palladium and Protium is that both hardware platforms share what we call solutions and peripherals. From emulation development kits and speed bridge adapters over virtual interfaces like accelerated verification IP, virtual bridge, and hardware-software hybrids, to, of course, memory models and even verification management and job scheduling solutions. Additionally, each platform offers some unique capabilities. On the Palladium side, that are, for example, the power verification and analysis capabilities, as well as a tight integration with coverage tools. On the Protium side, the ability to run interfaces like PCIe, Ethernet, USB in native mode, meaning at full line speed and without a speed bridge, further improves performance of the overall solution. All right. Back to you.
Thank you, Juergen. So now let's take a look at an example from one of our customer. Here you can see Mellanox, who is now actually part of NVIDIA, where they have a in-circuit setup. In this case, it actually works for both Palladium and Protium. Again, this is a real example where they're sharing the test infrastructure. And they have a host workstation here, the server, that basically allows them to transact the stimulus from the host back into the DUT through this PCI interface. And what's really beneficial for them is it's going to be very difficult for them to write a test bench that mimics exactly how this operating the system is supposed to work. The drivers, the actual drivers that runs on this host, as well as some of the software application that runs on it. So this test vehicle allows them to test their DUT as though it was actually now in their lab with their silicon. Now, of course, this is all done virtually, either in Palladium and Protium, and it allows them to do very accurate measurement of their behavior, and they can get functional checks as early as possible so that they have high confidence that when their design comes back and when the silicon comes back from the fab, it's going to work on the first day. And this is actually their goal, is to be able to do this when the silicon comes back, is to bring up the software stack on day one, right? This is kind of the industry gold standard now. Now, if you look at the details here, kind of like what I explained earlier, is the design goes into Palladium or Protium. There's a speed bridge in between the actual host, and then the drivers and the applications are being run on. So this is the key piece of the equation, right? Why would you need to rewrite all these complicated environment in a test bench in a system level, context? And so you're leveraging what's already available. In many cases, actually, they also need to do what they call backward compatibility mode. So even though you're creating a brand new design, but probably 50% or 60% of the software they're checking are about the compatibility of what's already out in the market. So it's very important for them to do this type of test. Next, if you look at the some other customers, so within NVIDIA, there's this graphics group that have done PCIe using virtual bridge environment. So instead of a physical connection through speed bridge, there's a virtual bridge in this setup. And here you can see there are two instances of PCIe. There's a UART, there's a JTAG, and there's a display RGB. And the design obviously is mapped, the GPU design here is mapped into Palladium. And this is a virtual machine that is essentially doing what the previous example was doing, where they have a drivers and an application, and is transferring the all the workload, all the stimulus into and out of the system, into the Palladium and out. While at the same time, they can use the UART port to do either JTAG port to do software debug. And again, this is really meant for a system emulation where they are trying to get the system integrated as early as possible, so then you can actually check for multiple operating systems. Here you can see Windows and Linux, and of course, the NVIDIA graphics chips are widely used across the different segments and industries, and so there's a lot of compatibility they need to ensure. They also need to make sure that the display, that they have, is creating the right image, right? So you need to have a system that are able to go through the different resolution, different scaling, different shadings, making sure that all the new algorithm that they have is done correctly. And so the engineers would visually inspect the outcome of those display, making sure that they are done properly. And then, of course, what's nice about this is the rationale behind why NVIDIA want to do this versus in circuit, which, by the way, they have been doing for the last many years, is the convenience. What they want to do is be able to load different operating systems virtually onto the virtual machine rather than physically, basically taking a hard drive out of the workstation, put in another version, or basically they have to reload an image, which is a lot of work for their IT or their engineers to do, right? So by having a virtual machine, they're able to manage all that complexity and be able to improve their efficiency. So that being said, so you can see there is a lot of goodness and using common methodologies to improve and automate the process. By having a unified flow between emulation system and the FPGA system, it gives you the ability to have very fast bring up, like Juergen was talking about. Because you're leveraging all the investment that you already made in Palladium, whether it's assigning the clocks, creating the memory models, running the scripts, having the right interfaces, etc. All the upfront work that you've done are automatically reused and transferred into a prototyping environment. And Cadence is obviously looking to make sure that we have congruency between emulation and prototyping, so it makes your job easier. And of course, if you're encountering a lot of hardware bugs in the protein phase or FPGA prototyping phase, it really means that your hardware is not stable. So you really should go back and actually clean that up before you move on to the software workloads, right? And of course, having a common front end allows you to reduce the learning curve, because once you learn how to use Palladium effectively, you know how to use Protium. And so that's a very good thing. And then having identical language support, right? So if you imagine you have two different systems with two different compiler, chances are you're going to have two different sets of language coverage. And that's going to be a problem as you're trying to traverse across different platforms. And so it's important to understand that having a common methodology will make your life and your company's life much easier. So overall, we believe we have the right platform, we got the right methodologies. We also have the infrastructure around this through what we call smart verification, so you can manage all the workloads, and not just across emulation or prototyping, but because we also have our simulation with Xcelium and formal through our Jasper Go products. And so you can see we have really a nice continuum of engines, static and dynamic engines, for you to solve your daily problems and basically find and fix most of your bugs and as much as possible and be as efficient as possible. All of these solutions, by the way, are also available in our Cadence Cloud, which makes it easier if you need the flexibility or some peak capacity. And again, this is something that we have been offering into the market for a while now. So hopefully this is useful and helpful for you to understand why a common methodology is important. And with this, I thank you for attending this tutorial. Thank you so much. Juergen?
Thank you also from my side. It was great being here with you today. And let's hope that we all see each other in person and live next year, 2022, at DVCon. Thank you.
All right. So long, everybody. Take care.